Balvinder Singh.
Yes, sir. Good
Okay,
evening, sir.
good evening. And Yachna, Yachna Nayar is available or not? I think it's not available. Okay, then we'll start for today class. Okay, the presentation is visible.
Yes, sir.
Okay, then the today topic is the georeferencing and some different georeferencing techniques which are used for different satellite image rectifications and other topography rectification. So georeferencing transformation image map from geometric coordinate system to geographic coordinate system. हेलो हाँ हाँ ठीक है गला ठीक है गला जी ऑनलाइन में प्रॉब्लम था तो then coordinate system geographic coordinate system using base map or image to image. So there are two type of georeferencing will be taken. One is from um, ground control points. So we just collect the ground control point, then georeference the satellite image or any other topo sheets or any maps. And another thing is then reference satellite image to other on reference satellite images. So these are two way. So image to image rectification is there, and then rectification through GCPs. So for rectification of different images, there are two basic parameters are needs, that is latitude and longitude. So latitude is generally the angular distance in degree, minute, seconds, or in the decimal format in of a point, and it is covering the north south of the equator. So these are all the latitudes, and line of latitudes are often referred to as parallels. So likewise, the longitude, which is also the angular distance in degree, minute, seconds of a point east west. It is spread in the east west direction, and line of longitude are often referred to as meridians. So these are called latitudes are called parallels, and longitude are called meridians. So the prime meridian is the equator. Then when the point is in the on the earth, then the point's angle is measured from the center of earth from the equator. So this is the latitude angle. So it is maximum 90 degree for one quadrant, and it is positive value. So in India, that is always the positive value of the latitude, also in the longitude. So longitude is the total swipe from equator towards the point. So this angle is called longitude, and this angle is called latitude. So these are the basic element to control all the maps and all the locations. So a lot of problems are there during the acquisition of the satellite images, and for the different along track, across track scanners are there. So during the scanning processes, a lot of errors also found. So when the image is acquired from satellites, then resulting images certain systematic and non-systematic geometric errors are occur, like sensor distortion due to some different defects or other movement and the velocity difference, then scan skewness, panoramic distortions, altitude of the platform. So a lot of errors are also found in different satellite images. So these are also corrected based on different techniques. So systematic distortions are like cross track scanners distortions, like some issue in the cross track scanner, then mirror velocity variations. So the actual velocity and nominal velocity differences. If the more, then there is the error is happen. Then scan skew, the scanning position, if it is deflected slightly, then it is also create an error. Then distortion evolved from a non-systematic distortions, the Earth rotation due to the Earth rotation, some distortions are there. Then altitude variation. Suppose some sensors are in 800 kilometer away from the Earth. Suppose the altitude is gradually decrease or increase. So at that time also some distortions are there, and ground resolutions are also varies. So pitch variations, suppose the track is slightly distracted, then spacecraft velocity differences and roll variations, the rolling of the sensor, then yaw variations, the actual ground coverage can be um, split in different directions. So this type of non-systematic distortions are there. Then systematic distortions are there. Suppose one input image, that is a raw image, need to be rectified. So there are some ground control point like GCPs are there. Minimum 4 points are there, ground control points. So it is transferred into the reference map. Then it is resampling. Then after resampling, the output image is referenced with respect to the Earth. So how the transformation model is there, what is the GCP's accuracy? So it depends upon the different data. So according to this, we have to correct all these informations. So there are minimum three type of polynomial orders are there to rectify these satellite images. So basically, we need a minimum 3 points to rectify an image. So the first order polynomial, the calculation is p, that is p point, p plus 1 into p plus 2 divided by 2. So for the first order polynomial, minimum requirement of the ground control points is 3, and for second order polynomials, minimum requirement of the ground control point is 6. For third order polynomial, minimum requirement of the ground control point is 10. So likewise, so different for if we increase the uh, polynomial order, then a lot of GCPs are required. So we generally need a third up to third order polynomials, because after that the skewness, the shape of the image is distorted. So a lot of up to 10 and 12 polynomial orders are there in different softwares. So we basically choose 2 or 3 third order polynomials, so that we conserve the shape and all the information in as compared to the real earth coordinates. So in the first order, the polynomial, the image is like this, and then second order, the sums uh, changes in the shape of the images. Then third order, the shape is drastically changes. So we have to try to get the georeferencing GCPs. Say we have to prefer the second order polynomials if the area is very good ground control points are there. So this is the satellite image which is not rectified. Then after rectifying with the reference of this ground control point, then it's look like the georeference data, georeference satellite image, and all the residuals, errors, and different positions, x, y pixel informations are there. So we can georeference all these images using AirDAS software or NV software, then RGIS also we can georeference, then QGIS. So a lot of softwares are there. So minimum requirement of the ground control point is three. You can choose 4 or 5 points. So this is an example of georeferencing some vector file. So from the control point. So if the actual position of the point is in the green plus line and the reference point is there. So this is the error we found in this georeferencing tool. So this error need to be minimized so that our observation and our calculation of different features is geographically corrected. So these are some theories that x dash is equal to ax plus by plus c and y dash is equal to dx plus ey plus cf. So where the xy is a calculated x coordinate of the pixel of the map, then y1 is the calculated y coordinate of the pixel of the map. So these are the some calculations, though these are not needed. But this is very important. That is first, what is first order polynomial, what is second order polynomial, what is third order polynomial, then the calculation method, which is the calculation method, then how the polynomial different polynomial changes according to their ground control points, and what is the benefit and what is the disadvantages of taking more than 10 ground control points. So how this effect, and what is the situation where we can get more ground control point, and which type of satellite image or maps needs less ground control point to get the accurate georeferencing information. So interpreting the root mean square error. So overall, after georeferencing all these satellite images or any maps, so there is some error is there because it is not accurately georeferenced with respect to the Earth. So it shows some error. So it can be minimized and it can be uh, acceptable due to some software issue and some real world and virtual earth have some differences. So when the general formula is derived and applied to the control points, the measure of the error, the residual is also returned. The error is also difference between where the point end up as opposed to the actual location, and this value describe how consistent the transformation is between the different control points. When the error is particularly large, you can remove. When uh, taking the process of geoprocessing, if you got the more error, then you can delete these points or the links. Then you create a new points to georeferencing these images. So although the RMS error is a good assessment of the transformation accuracy, so it is also showing the what is the accuracy of my georeferencing processes, and is it acceptable for me or not. So it's also give you the sign for the correctness of the georeferencing images. But after georeferencing the images, it's still gonna some errors. So it will be further evaluated with respect to different points. Then resampling methods. So there are three methods are there. This is the desirable if nearest. That is one of the resampling is nearest neck boring. So nearest neck boring resampling determines the pixel value from the closest pixel to input coordinate specified. So in the resampling method, suppose we get the georeferencing data. So the reference pixels near the from the reference satellite data. So it takes the nearest pixel information from the reference satellite images so that it is corrected and assign that value to the output coordinates. So this is the nearest neighbor. Then bilinear resampling, where the resampling determines a weighted average of the four nearest pixels. So it take four nearest pixel, then the average of the pixel is calculated, then it is corrected according to this. So closer the center point of the pixel, the greater contribution or weight it will have that final DN value to be assigned to the correct pixel. So this is not recommended if classification is followed. The new pixel value may be slightly different from the actual radiance value, and the computation time of this specialty is about 10 times greater than of nearest main neighbor methods. So generally we take the nearest neighbor method for calculation, and in the nearest neighbors it provides a slightly sharper image than the bilinear method, and you also corrupt the original pixel values. So some positive and negative value advantages and disadvantages are there. Then what is the data format? Different data format of remote sensing satellite images are there. So first, the process is the image acquisitions, image processing, image classification, then accuracy assessment. First, we have to acquisition of this image, and different image processing techniques are there. Then we have to classify the different features of the image. Then after classifying, then with the classification technique, then we have to assessment of the accuracy of the classification technique. So these are the methods. So first of all, we have to go to the georeferencing technique, just like so. There is a topo sheet. So every topo sheet have their name. It is a 1:50,000 scale topo sheet of Survey of India. So basically, in the topo sheet, uh, the latitude longitude informations are there, and the grid size, these are the grids, and the grid naming is that F45P2. So this is the F45P2 grid, and it is in the Odisha coast near the Balesar district. So in the topo sheet, there are a lot of information like topographic informations are there, like river, then agricultural land, road, canal, railways, settlements, then forest area, that is RF. What is RF? That is reserve forest. Then different. This line is the intertidal line zone. So this signifies that the tidal influence water body is present there. So from the sea, there is a tidal influence in this area also present during high tide line, and during the full moon, and then time this the high tide is more. So there is the tidal influence also present in these areas. So likewise, there are and there's a sand area, and these red dots are settlements, and these green boundaries are the reserve forest areas. A lot of informations are there. That these are the, taking as the best make for different applications, and the accuracy is very high uh, of this reference data, as it is from the Survey of India topo sheet. So there is then the district boundaries are also there. Then this is the district boundary of Balesur district. So there are 4 points are given in the top corner of the tower, on four sides of the opposite, that is 21 45, 21 degree 45 minute. So this is the latitude informations, and for 87 degree 0 minute, that is the longitude information. So the latitudes are, these are the latitudes and these are the longitudes. So it is increases right towards the right sides, and the latitudes decreases towards the south, so towards the downsides. So it is a 15 minute and 15 minute grid, because it is the just it is the 87 degree 0 minute. So its end is 87 degree 15 minute. So it is a 87 degree 15 minute. So 1 degree is about one 110 kilometer. So it is a 15 minute means it is nearly 27 kilometer into 27 kilometer, approximately 27 kilometers. So we have to calculate after that registration of this georeferencing of this opposite. So first of all, we have to add this data to our RGX platform. So just add. So when adding this data, it is shown that this is an unknown spatial reference. So it means that the data is not referenced with respect to the this windows, and this is the reference data. So we have to add this. We just right click and zoom to layer. So this is the data. So in this lower side, there is no information of latitude longitude information. So after getting the georeferencing of these images, we get the latitude longitude information correctly. So for georeferencing this satellite image, there are sorry, this topocid. So we need to reference this latitude longitude information. So there are 4 points. So we need to rectify these 4 points using georeferencing tool. So there is a georeferencing tool. By right click this, we have the georeferencing tool. Georeferencing tool is there. So it is a georeferencing tool. Then we have to activate our toposit. Then this is the add control points is there. We have to georeference by using add control point. So there are various links are there. So there is no any links is present. So after taking these points, then links is shown. So we have to zoom it, then take 1 point from left click, then right click it, then click on input degree minute second, that is DMS, then just input all the information which is given. This longitude is 87, minute is 0, second is 0, then it is in the east, and latitude in the north. So then latitude is 21, then it is 45, then second is 0. So the first point is completed, then we have to click on OK, then zoom to layer, then 1 point is completed, then second point. So another click on the add point, add control point. The same trigonometry is required for these areas. So input EMS, longitude is 87, then minute is 15, second is 0, latitude is 21, it is 45, then it is 0, is okay. Then only rest 2 points are there. Longitude is 87, then 15 minute, then it is 0, then it is 21, 30, 0. The another last one is there. Okay, then it is rectified. So just click on georeference. You can rectify it. So nearest neighbor generally we consider bilinear interpolation, cubic convolutions are there. So just go to the output location, then save it in the topo sheet, then rename it as rectified or georeference, anything you can take. Then it can be TIFF file or IMG file. So just take it as a TIFF file. So it is your reference. Then all this data. So this is RMS error. And so it is less than 1. So it is considered as one of the good georeference. Then these are also first order, second order polynomials. If it is not satisfied with the 4 point, then you can take more than 4 points and using second order polynomials. So I think we have to object georeference. So it is now compare with our satellite data. So this is our satellite data. Then this is our, so it is georeference with respect to our satellite image. So it looks like it's a, now it is, because reverse position are different for different time zone, so it cannot be accurate. But just go through this. This is the short line. Okay, so it is now georeference. So this is the process of georeferencing using ground control point. So if we have some satellite image having there is no uh, ground control point, then we can reference it within the satellite images. Suppose I have a satellite image of same area. Just a minute. Suppose this is the rectification using GCPs. So suppose we have to rectify this area, this satellite image. Just add. This is our unrectified Google image. It is not rectified. So we have to rectify it with respect to our reference satellite image. So we have to choose what is the ground control point, what is the common points between two satellites. So to first identify the common points, I think this is one of the common point. this data, this is our point. So in this area, there's a Google image. Just take this area and go to the bookmark. Then just add the first map. So this is the point. Just click then and go to the next point. And this is also one of the control point. This point. Same point. So it is now transferred to this area. Then we can check the data. So it is not corrected. We have to choose another point. Then this rectified. Likewise, you can rectify image to image correction by identifying the same common areas of different satellites. So this image is highly high resolution satellite image collected from the Google Earth. 1, 2, 3. So this is the 10-meter resolution Sentinel data, and this is our Google Earth image, which is very high resolution as compared to this satellite data. So we can get the different site high resolution data using the Google Earth image by the techniques of georeferencing for different patches. So in the Google Earth image, we cannot get the big areas. So for small areas, we can georeference, then we can mosaic or join all this. So it is now get the georeferencing images. So this red color is a false color satellite image, which has 10-meter resolution. Now it is clearly visible with the Google Earth image. So we can analyze but we cannot calculate different remote sensing analysis because it is a image and there is no spectral bands are there. But in the sentinel data, there are a lot of spectral bands and DN values are there. But it look like then just a image. That it's not like the other satellite image. For identification and classification of different features like land use, land cover, we can use this, or for road network drainage, we can also use this. So these are the two method where we can reference the data like toposheet, how to rectify using GCPs, then image to image rectification, from lower resolution of image to high resolution of image can also be rectified, or high resolution satellite also get taking as the reference, and low resolution satellite also rectified as compared to the reference images. So these are the techniques, and these are used as per your requirements. And there's a need for urban planning or urban plan classifications, you can use the high resolution satellite data, which is if not available to you because a lot of high resolution satellite data are commercially available and not free of cost. So you can use these techniques for classifications. For water resource analysis also you can classify. But for supervised and unsupervised classification, it may be difficult because the exact DN values are not present in this Google Earth image. But you can classify the satellite image. And another thing is that that opposite numbering. So one slide is there, how to get that opposite numbering. So UTM grid, UTM means universal transverse marketer is there. So in this method, so total India is divided into different grids. So 4 minute into 4 degree into 4 degree grids. That is a 4 degree, and I think it is a sorry, 6 into 4 degree grid. The 90, 96, 6, and it is 32, 28. That is 4. So 6 into 4 uh, rectangles are there. So the whole total India is covered within this grid. So these are the numbering F45, E45, which are F44 and E44. These are the grid from which the Odisha is covering. So this is the UTM grid. Then it is further divided into different parts. So it is the polychronic grid index, where old toposit grids are divided into 4 minute into 4 minute grids. So this is 6 into 4, and this is 4 into 4. So there are two type of numberings are there. So in this, the 64, 65, 73, 74 is the Odisha grid system is there. So suppose there is a opposite numbering 73 H12. So it is coming from the 73 grid, then it is divided into 16 grid, that is uh, just taken into there. So this 16 grids, from this the H grid is present. So from this H grid, then again this H is divided into 16 grid. So 73 H12. So this is the numbering, polyconic numbering of the different opposites. Then this for further classification of 7.5 into 7.5, there are four classification, that is northwest, northeast, southeast, southwest. So these are the numbering. And for the 16 grid, sorry, the 6 into 4, So that opposite, this is the old grid numbering system, 73 L by 5. So this is the numbering. Then the new grid system, F45P2. So these are the numbering system of the opposite grid. This is the open series map, and this is the new series map numbering of the survey of India opposite. And it is, I think, created in 2011. First edition is 2009, then 2011 is also there. But these are the opposite of 1986 or 88, I think. These are the old opposite grids. The year is not available, I think. So on 1980. This is the 1980 opposite grid, and these are the 2009 opposite grid. So these are the old series and open series opposites, and these are the very clear demarcation of different features. But the contours points are not presented in this grid, but previously the contours are there. Not, these are the contour points, which signifies the height of the location, and the 100 meter and 60 meter, 124 meter. These are the height information, and it is signifies the height of the features. These are the contour points. So this is about the georeferencing and all about the referencing techniques. Then we have some image acquisitions. So there are three type of image acquisitions are there. Suppose these are the bands 1, 2, 3, 4 of different satellite images. So each band have some DN values arranging in different rows and columns. So that digital number of column 5, like of row 4, column 5 and 4 at band 2. So for the band 2, this is the band 2 of for column 5. This is the 5, and the row 4. This is the row 4. So 105. This is the value of the pixel and DN value. So it is expressed as the references BV 542. So column 5 and row 4 and band 2. First is the column name, second is the row name, and third is the band name. So a lot of bands are there, 5, 7, 10, 12 bands are there. The value is 105. So this is the matrix format pixel related satellite images. And then different image formats are then BSQ, band sequential format, band interleaved by pixel format, then band interleaved by line format. So each in the band sequential format, each line of the data followed immediately by the next line in the same spectral bands. And for the band interleaved by pixel format, the first pixel of all band in the sequential order, followed by second pixel for all band, then third pixel of all band, interleave up to the number of pixel, how much bands are there. In the band interleaved by line format, the first line of the first band followed by first line of the second band, followed by third line of the third band. So generally, it is also asked in exam what are the format image file formats. So these are the three important file formats. So I'll provide this PPT. You just go through it. So this is the example. How the arrangement of the bands pixels are there. So for the BSQ, it is and these are the band 1, band 2, band 3, band 4. The uh, first row is represented there. Then second band first row, first column. Then third band first row, first column. Then fourth band first row, first column. Likewise, these are arranged in this sequence. So in the BIP band interleaved by pixels, the first uh, band of first row first column, then second band first row first column, third band first row first column, fourth band first row first column. Likewise, they are arranged in this line format. Then band interleaved by pixel, then band interleaved by line, first row first column of the first band 10, then 15, 15, 20. These are all uh, collected in the line first line, then 15, 16. All these first bands are collected here, then second band collected here, then third collected here, then fourth collected here. So it is band interleaved by line. So at one line, all the bands informations are there. So you can correlate all this with this definition of the band BSQ, BIP, and BIL with these images. So likewise, these are the some example band sequential and band interleave. So in this band sequential image, one band at a time. In other words, the data for all pixel for band one is stored first, then data for all pixel for band two, likewise. So in the all pixels for band one are stored in the first, then second, then third. And when interleaved by pixels, data is similar to the VIL data except that the data for each pixel is written band by band. For example, with the same three band images, the data for band 1 to 2 are written for the first pixel in column. So these are the band 1, band 2, band 3, band 1, band 2, band 3. So first row, band 1, band 2, band 3. This is the 1 pixel. Then this is the pixel 2, band 1, band 2, band 3. So these in this way they are the arranged. But in the last one, then band 1, band 2, band 3. So it is in the line format, band 1, band 2, band 3. So 1, 2, 3, 1, 2, 3. Then it is a 1, 2, 3, 4, n. So it is in the line format. It is generally in a vertical format. It is in the, sorry, it is in a horizontal, it is in vertical, and it is in mixed format. So you can go through it, then you will easily understand this. So before going to the final processing, there are the image pre-processing is there. That is a geometric correction already discussed on the georeferencing. Then radiometric correction is there. Then atmospheric correction are there. So it's make it easier to interpret using image enhancement. So some of the images are not actually ready to use after acquisition of the data. So after geo corrections, then radiometric corrections are needed, then atmospheric corrections are needed. So in the radiometric correction, the radiometric pre-processing method are constructed physically calibrated value by correcting the spectral errors like in the image. This is the radiometric errors are there. The figure shows the typical system error which result in missing and defective data along a scan line. So these are the defective data. So drop lines are normally corrected by replacing the line with pixel values in the line above or below or with the average of the two. So by averaging the value of the pixel information, we get the data corrected data. But during this radiometric correction, we just lost some of the pixel informations. So it also affect the analysis if we use for the correct, highly accurate analysis. So because this is some of the pixels are average of the nearest pixels, so we just lost the actual information of the data. But as there is no available of substitute for this image, so we can use this, and it can get good result as compared to the old data. Then there is a speckle noise removal, so this image is not clearly visible, all the informations. So this speckle noise are removed, and after that, the clear rectified image are getting from this process. So in the atmospheric correction, solar radiation is largely unaffected as it is travel through vacuum of space. A lot of atmospheric uh, effects are there. So after different layers of atmosphere like troposphere, stratospheres, mesospheres, thermospheres, so a lot of distraction of the radiations are also possible. So it is interact with Earth's atmosphere. It is selectively scattered, and sometimes the scattered of the wavelength, and sometimes the sum of the EMRs are absorbed. So the sum of these two form of energy loss is called atmospheric attenuations. So when the process of scattering and absorption of this EMR, which is coming from the space, is atmospheric attenuations, and the general goal of atmospheric correction is to turn the digital brightness value, that is the DN number, recorded by remote sensing system, into scale surface reflectance values. So this value can also be compared and used in conjunction with the scale surface reflectance value obtained anywhere else on this planet. So different scattering, absorption, refraction, reflections, which are gone through the different sensors. So these are several way to atmospheric correct remotely sensed data. Some are relatively straightforward, while others are complex, being founded in the physical principles and requiring significant amount of information to function properly. So this is one of the example. It is the atmospheric correction due to the substantial haze prior to the atmosphere. Some haze are there in the satellite image. So before atmospheric correction, the images looks like this. So after atmospheric correction, the haze part is corrected, then it is clearly visible as compared to the previous data. So different models are there present for atmospheric correction, and it is also freely available. Tools are there. So one of the tool is ETCORE, that is useful for the atmospheric correction. So a lot of things are there, but we have to get the parameters, which different satellite parameters are required for the correction of the atmosphere. This is the at core, and different parameters are analyzed like BSQ and internal orientation, quick loop, additional data, external orientation, digital elevation model, value added product, then the sensor characteristics. So after that, we can get the reflectance and reflectance satellite images. So these are the software tools, and then the different level of product are there. Level 0 product of satellite image, level 1 product, and level 2 product. So we'll discuss different level of products later. So based on the different corrections, the different applications, the different products levels are there. So the modification of image to alter its impact on viewer, interpreter, enhance. So enhancements is very much important, because sometimes we cannot see the different features. With the help of image enhancement, we can get the informations. So this is very much useful for an analysis of the different features and objects. The process of making an image more interpretable for particular application to attenuate the certain image features, then attempted after image is also corrected and maybe performed temporarily or permanently. So there are various enhancement types are there, like a radiometric enhancement, spectral enhancement, and spatial enhancement. So in the radiometric enhancement, modification of brightness value of each pixel is an image dataset. Then spectral enhancement, enhancing image by transferring the value of each pixel on a multi-band basis. Then spatial enhancement, that modification pixel value based on the value of surrounding pixels. So these are the techniques we can enhance the data to form analysis of different applications. So these are all the remote sensing technology and remote sensing tools for the enhancement. After that, we use the GIS tool to analyze different parts. So generally, radiometric enhancements is the modification of brightness value of each pixels in an image and bright out contrast in the image applied separately to each band of data. So enhancement applied to one band may not be appropriate. So contrast enhancement, these are the radiometric enhancement. So in a image enhancements improves the interpretability of the image by increasing apparent contrast among the various features. So contrast manipulation, contrast stretching, special features manipulations, multi-image manipulations. These are the important thing which are required for the image enhancement. A reason for the low, why the low contrast are there in the satellite image. So various reasons are there. So one of them is sensitivity of the detectors. So it depends on the sensor to sensitivity of this subject. So some remote sensing system may lack sufficient sensitivity to detect and record the contrast of the terrain. Suppose it is dark, it is what is the darkness quality, or if the brightness is not accurately detected and it is shown in the wrong way like dark objects. So detector on the most sensing system are designed to record a relatively wide range of scene brightness values, so without becoming the saturated. However, the few scenes are also composed of brightness value, and the atmospheric scattering also one of the problem, that is scattering of the electromagnetic energy by different atmosphere can also reduce the contrast of the scene. And of course some of the haze and some of the atmospheric condition in the lower earth also one of the problem. So contrast enhancement is the difference between the average gray level of an object that's surrounding. So generally the enhancement of the contrast in the satellite image keep the details clearly visible of the detailed subjects. So just enhance the pixel information values to a uniform way. So that is the contrast enhancement. So the formula is the contrast for the maximum gray value by minimum gray value. So where is the DN value is sorry, the reflectance value increases from 84. So 153, 84 started from 84 and in the 153 in the original image, then it is stretches from 0 to 255. So for in the 8-bit computer, that is 0 to 255 mm, range is there. So it is traced uniform way from lower to highest level, so that the original image converted to these stretch images and it looks very clearly visible objects as compared to the original image. So for image interpretation, we can change the contrast of the satellite images if needed. So it's not compulsory to enhance the contrast of the satellite image. Sometimes it is needed, or sometimes it is not required. So based on the availability of the satellite image, we can enhance the contrast, or otherwise it is not useful. So this the linear contrast is there, and the density value is inherently pulled further apart and then expand over the great range. There are two type of contrast states, like linear contrast states and non-linear contrast states. So minimum maximum states and standard deviation states, piecewise linear states, sawtooth states, different states are there. Then logarithm in the non-linear contrast, inverse log, exponential, square, square root. These are the non-linear contrast. After that, we have some level and different level data, that is level 0 data, level 1 data, then level 2 data. So basically we found in the satellite image, and there are three type of data. We can also get the data in the Google Earth engine or USGS site. These three type of data are there. So what is level 0 data? So these are the unprocessed data directly from the satellite sensors. Contain all the sensor reading in their original format, including radiometric, geometric, and ancillary data. So it is also includes telemetry data, might have data gap or noise. So these are the raw data which is not rectified in terms of atmospheric correction or any radiometric corrections. So these are the level 0 data. So generally, these are not available for direct use by most of the user, or primarily written for internal processing purpose. You can also use by using different filters and different. If you have any skills, then you can uh, atmospherically corrected this data. Then radiometric correction, you can go through this. Then level 1 data is systematically corrected data that is undergone geometric and radiometric correction. So in this level of data, we undergone the geometric and radiometric corrections as divided into two primary product. There is level 1T, that is terrain corrected, and level 1GT, that is geometrically corrected without terrain corrections. So level 1T is geometrically corrected to standard map projection using ground control points, and digital elevation models are used for the correction of this data, and it is most common product we use for most remote sensing applications. And what is the 1GT? Level 1 GT, that is geometrically corrected using satellite ephemeris data, but without the use of ground control points of them. This data has low positional accuracy, that level 1T. So level 1T is very geometrically corrected data, and GT is not as per the definition. So this data lower positional accuracy, that level 1T. So it provides that is geometrically calibrated and orthorectified when it is adjusted for geometrical distortion caused by the sensor satellite movement and terrain elevations. So 1T and 1GT is very much important. So level 1 data is generally useful for our different applications. Then the level 2 data, the product which includes higher level of correction like surface reflectance, surface temperature data. So this is the level 2 data. So it includes atmospheric correction to remove the effect of atmospheric interference, haze, cloud, convert the data into surface reflectance value, then surface reflectance product that convert top of the atmosphere reflectance to surface reflectance by correcting the atmosphere condition. In surface temperature product provide estimation of surface temperature. So generally the level 2 data is often used for the application that require accurate surface properties such as vegetation monitoring, land cover classifications, change detection, thermal classifications. So in the level 2 that data there is no need of any atmospheric corrections. So already they are in this level 2 data. So we have level 0, level 1 and level 2 data. So they are the general question also may be asked for this chapter. So when we're downloading the raw data from USGS site, or we just order the satellite image, then this is the satellite naming are there. The satellite image namings are like that. So what is the naming? Then all these codes are have some meaning. So this is the LC, that is the Landsat sensor data, that is combine both OLI and TRS. What is the OLI? OLI means operational land imager, and TIRS is a thermal infrared sensor. So LC data, it is combine of OLI and TIRS. 08 means it is the Landsat 8 data. Then L1 means that is the level 1 data, which is also discussed before. Then TP, that is terrain precision data. And if it is GT, then it's a systematic terrain. If it is a GS, then geometric systematic. So this is the terrain precision. Then this is the code is the wide reference system. This is the just like latitude longitude information 27 degree something minute. So this is the worldwide coding system, that is the reference coding system. Then data acquisitions date, so it is reversely written, that is 07 7th February, that is 02 2017. So this is the data acquired. Then the data product generated is 16 February 2017. So this is the generated data. Because it is a level 1 data, so level 0 to level 1 it takes 8 to 9 days. So it is then it is level 1, 0 of code is there. Then collection category is a T1 collection. So these are the information which are given in each of the satellite images which are downloaded in USGS or any other platform. So it should be remembered that these are the information. So at least the date and the Lancet type we can remember. So while reference system is not required, so we have to remember that it is a level 1 or level 2 or level 3. So this is the level 1, then it is a Lancet, and this is the date. So these are three important in metadata information of the satellite data. So the processing timing, suppose the Landsat 7 and 4 days is required for ancillary data, level 1 data, then level 1 to level tier 1, tier 2 is needed 24 days, and tier 2 to level 2 that's 24 hours. So these are the dates for different applications. So these are the non-linear contrast enhancement and gamma states. So we'll discuss in the next class. So for today it is uh, completed. So okay, then is there any query? Okay, then we'll close the session. If any doubt is there, then you can ask. If you need this uh, slide, then I will provide you.
Yes, sir. Sir, please share the slide and sir, the slide of the map sheet numbers, old and new one.
Okay, okay,
Sir, thank
okay.
you, sir.
Then Yachna, are you there?
Yes, sir. Good evening, sir.
Good evening. So we have some idea about the georeferencing technique now.
Little bit, not that much. I have to learn more. Actually, I have to practice more. I'm not that much familiar with these techniques.
Okay, but this is the basic technique. So just to know this.
Your voice is, I think, some distortion is there.
No, from other side, I think other people are there. No, from my side, it
Maybe
is
from
fine.
Manish side.
Okay. Okay, Manish, it is. I think you have some experience in this area. So, Yachna, you have to do. Okay, Manish, tell me. Okay, then we will close this session. So, next class we will discuss all this rest of the topic.
Okay, sir.
So,
Thank you.
Thank you, sir.
thank you. Good night.